Hi everyone, today I'll be talking about the work Hypercontractivity of High-Dimensional Expanders. This is based on joint work with Tom Gore and Noam Lifshitz. So let's start with motivating a bit why we want to prove hypercontractivity inequality. Okay, so it turns out that the main motivation here is that hypercontractivity inequality can help us show that certain graphs are small set expanders. We say that a graph is a small set expander if every small set of vertices in this graph has most of its edges outside the set. So an example is below. Here we see a small set expander, and if we look at a small set of vertices in it and look at all their adjacent edges, we'll see that most of the edges connect the vertex to another vertex outside the set. So these are called edges outside the set. We can see here that most of the edges are actually outside the set. So this is such an example of a small set expander. And the reason we want to study small set expanders includes some of the following. So first, there is the hope that small set expanders with many large eigenvalues can give us hard instance for showing unique games, for proving unique games conjecture. And also, in some recent work in showing that 2-2 games conjecture is true, small set expanders property are used in analyzing certain agreement tests on the graph. So in this case, specifically for the Grassmann graph, satisfy some soundness restriction, some soundness condition. So essentially, this is helpful in proving agreement tests have soundness on graphs. Okay, so now let's move on to what precisely are the formulation of hypercontractivity inequality. So we consider a probability space E comma mu, where E is the state space and mu is the probability distribution associated with the space. Let's say the state space is over k variables, k random variables. Then we say that the space E mu is hypercontractive if there exists some function C, which is an increasing function, such that for every function f with bounded L2 norm defined on this probability space, we have that the force moment of the function f is upper bounded by the function c applied to the degree of the function f times the second moment of f squared. Okay, so let me first explain that this notation fp to the p is essentially the piece moment of the function f under the distribution mu. And to give some intuition as to what hypercontractivity inequality really is saying about the probability space, let's see the following kind of reasoning. So let's say that the function f has a degree decomposition of the following form: summation over all s, which are subsets of the entire set of variable 1 through k, cs times f of s. Here we consider f of s to be let's say it's an orthogonal decomposition, and the function f corresponding to the subset s has degree precisely the cardinality of the set s. Then we can write, since it's a orthogonal decomposition, we can write the force moment of the function f to be equal to basically summation over all s, cs to the 4 times the force moment of each individual component f of s force moment. Okay, so in this case, we also want to note that the force moment operator basically blows up those very spiky functions. So if a function is very uneven, very not smooth, then this for norm would blow up the function a lot relative to the force moment will be much larger than the second moment square of the function. Okay, so it means that if we want to show a hypercontractivity inequality for a space E mu, it would be bad if the low degree functions are very spiky. And the reason being that for low degree functions, the function c degree of f will be a relatively small number. However, on the other hand, if the low degree function are spiky, we know that the force moment will actually be much larger than the second moment square. So it will be hard to come up with a C that's large enough for a small degree so that this hypercontractivity function still hold. Usually if the function C is too large, we wouldn't consider this probability space to have a hypercontractivity inequality. Okay, so what this whole argument is saying is essentially that hypercontractivity essentially implies or is equivalent to actually saying that low degree functions over the probability space are smooth. So they're not spiky. So this is the intuition behind a hypercontractivity equality. So let's see an example of hypercontractivity equality. The most, I guess, well-known example would be the Bonami lemma, which essentially is considering the probability space of the uniform distribution over the Boolean hypercube. So it says that for every function f with bounded L2 norm over the uniform Boolean hypercube, we have that the force moment of f is at most 9 to the degree of f times the second moment of f squared. So the degree decomposition for functions over the Boolean hypercube is precisely the Fourier decomposition. Here we have chi of s being the Fourier character and the f hat of s being the coefficient, Fourier coefficient. Since we have this hypercontractivity for this uniform Boolean hypercube, we essentially know that low degree characters over this domain are actually smooth. Therefore, by contrapositive, this is saying that those functions that corresponds to small sets, which essentially says those functions are very spiky because they correspond to small sets. Those functions need to be of high degree. Okay, and furthermore, if we use some more Fourier analysis technique to analyze associated noise random walk on the hypercube, we'll realize that the small subcubes precisely corresponds to those least expanding sets in the Boolean hypercube. And therefore, from there, from analyzing these small subcubes expansion, we could deduce that Boolean hypercubes are actually small set expanders. But okay, the second step, I won't really be talking too much about here. They're not quite relevant for this talk yet, so I'll leave it to that abstraction level. Okay, so next I want to summarize some of the known hypercontractivity inequalities over various probability spaces. Here's a table. So in this table, one thing I want to comment on is this degree function CD. So because there are multiple equivalent, well, not quite equivalent, multiple like slightly different formulation of hypercontractivity inequality. So some of these work are actually given in some of the other formulations. So we try to convert them all into this specific formulation hypercontractivity inequality. So there might be kind of loose steps that we take so that the CD here doesn't reflect the optimal C of D function in these works. So I just want to make a comment there about this. Okay, now let's look at all these results. So the first two lines, the first line is just a Bonami lemma that we just saw, and the second line is due to Kivish et al., who proved a hypercontractivity inequality over the non-uniform Boolean hypercube. Despite it being non-uniform, it gets basically binomial distribution, so it's still a product space in some sense. And these two product space domains both get some hypercontractivity inequality, and the intuition there is that essentially product space can be thought of as a generalization of the Boolean hypercube. We just replace the Fourier analysis technique there with some generalization of the Fourier decomposition into the product space. This decomposition now has the name Efron-Stein decomposition, and many of the steps still go through. So in general, for the product spaces, we do have some sort of hypercontractivity inequality. So this is intuition for these first two lines. And next, we see the next three lines. Next three lines, okay, this result due to Thomas et al. Is showing hypercontractivity for the symmetric group distribution, and O'Donnell-Wimmer showing it for Boolean slice, and the Thomas O'Donnell-Wu showing it for multi-slice. So these distributions, these three distributions all have the property that they're actually non-product spaces. So this probability distribution is not a product distribution, but in some sense, they're actually kind of close. In what sense, I will talk about later. But since they're, as we say, although they're not product space and therefore Fourier analysis doesn't directly apply, and doesn't generalize nicely, people are still able to show that they have hypercontractivity inequalities. So this leads us naturally to the question, which is, can hypercontractivity be generalized to those almost product space? Turns out that the answer is yes, and we show it specifically we show specifically that this inequality is generalized to what's called a epsilon product space. So we all know a product space looks something like the following. We have a basically we have a domain space E, which is equal to V to the K, where V is the domain for just sample space for just one random variable. And the associated distribution, probability distribution, is a product distribution. On the other hand, for epsilon product space, we relax this condition a little bit so that mu doesn't have to be a product distribution. And instead, we ask mu to satisfy the following requirements. So consider all the conditional distributions where we condition coordinates in the small subset S being assigned some value X. And then in this resulting conditional distribution, we require that for any two free variables in this conditional distribution, the two variables has correlation bounded in absolute value by the number epsilon, by the value epsilon. So in some sense, this is saying that all the conditional distribution need to be close to being pairwise independent. So this is the relaxation we made. So they can be not exactly independent, but they need to be close to pairwise independent. And the closeness parameter is epsilon. The smaller epsilon is, the more independent these two numbers are, or these variables are. Okay, so it turns out that what we've shown before, the symmetric group, the multi-slice, the Boolean slice, they're all like they all are epsilon product space, but not just them. It turns out that the very interesting domain of epsilon high dimensional expander also gave rise to some epsilon product space. And to show that, I'll briefly talk about the definition of epsilon high dimensional expander. So an epsilon high dimensional expander essentially are hypergraphs with an associated edge distribution E mu over size K hyperedges. So let's see an example. Let's say we want a dimension 3 hypergraph, and therefore this K in this case will be equal to 3. And the edge distribution we get is a distribution over three random variables. And each random variable can take on value corresponding to the vertex label of any vertex in this graph. Okay, and the distribution mu basically gives a distribution of all the, it's a uniform distribution over all the size K hyperedges inside this hypergraph. One comment I want to make is that these hyperedges corresponds to unordered sets, like 1, 2, 3 here. This is an unordered set. But our probability space naturally induced a order over all the vertex labels. So how we solve this problem is just by having mu, by taking a hyperedge, for example, 1, 2, 3, and basically split its probability uniformly at random over all the possible orderings of these three vertices. So in this way, we basically induce a probability space mu over all the ordered sets of hyperedges. Okay, so this is how we define the distribution over hypergraph. But for a graph, hypergraph to be epsilon high dimensional expander, it also need to additionally satisfy some expansion constraints. Precisely, it need to have the following property. It need to have link expansion at most epsilon for every edge. So what does that mean? So without loss of generality, let's consider one edge. Let's say the edge 2. And then what we do is we look at all the hyperedges inside this hypergraph that contains this edge 2. So they're all colored in green now. Then we take out all these green hyperedges, and they basically constitute a new hypergraph. And we remove from every hyperedge in this new hypergraph the edge 2 itself. And that gives us this hypergraph on the right-hand side. Okay, and essentially this probability distribution E induces a conditional probability distribution E prime over this new graph, because we can say that these hyperedges here inherit the probability distribution from this larger hypergraph before. And then after we are left with this new hypergraph, we look at the size 1 edges, essentially these vertices, and the size 2 edges in this graph, and we look at the bipartite graph induced between these two size sets of different size hyperedges. And these edges are basically representing inclusion relationships. And this bipartite graph help us to define the link expansion the following way. So the link expansion of this specific link of the edge 2 is equal to the second largest eigenvalue of the bipartite graph of this specific bipartite graph. And we say that the link expansion is at most epsilon if the second eigenvalue of this bipartite graph is at most epsilon. So essentially, the smaller epsilon is, faster random walks on this bipartite graph would mix. Okay, so for a hypergraph to be epsilon high dimensional expander, we essentially need all the edges link to have expansion at most epsilon. Okay, so this is the definition of epsilon high dimensional expander. Now we want to check why epsilon high dimensional expander are actually epsilon product space. So we check the definition line by line. So first, I guess both epsilon high dimensional expander gives us an edge distribution, which would be the probability space that we will be considering. And next, in the epsilon product space, we require that inside this conditional distribution, all free random variables need to be close to be pairwise independent. And equivalently here, we just require all the link distributions in the high dimensional expander to satisfy that a link expansion is at most epsilon. So I will not go through this too carefully, but if one takes some time and stare at the definitions, one will see that these two requirements here, this conditional independency and this link expansion, are essentially equivalent for the case of epsilon high dimensional expander. So I would just jump to the conclusion, which is that epsilon high dimensional expanders are actually epsilon product spaces. Now I'm ready to state this main result of our work. Our main theorem says that for any epsilon product space, E mu and F of bounded L2 norm over the space, if F is of degree D and satisfies certain nice smoothness condition, then we have that the force moment of F is bounded by this 400 times d to the power of d times this delta. This is our niceness parameter times the second moment of F plus some small error terms that's related to epsilon and delta and F to second moment. Okay, so this would basically as a corollary, we would know that such a hypercontractivity inequality also hold for the edge distribution induced by epsilon high dimensional expanders. So before talking about the proofs and even this specific definition of this part, I'll mention that there's a concurrent work by Buffna, Hopkins, Kaufman, and Levitt, who also obtained the same result via different techniques. So both of our work essentially relies very crucially on a decomposition of a function f on this over this product space, over this epsilon product space. But the difference is that Buffna, Hopkins, Kaufman, and Levitt, they obtained this decomposition using random walk operators to find out high dimensional expanders. Well, in our case, we generalize the Efron-Stein decomposition over the product space and obtain a decomposition for epsilon product space. So this is the main difference. Okay, now before talking about the proof, I will explain more what is this niceness condition that we impose on here. So if we recall at the very beginning, we mentioned that basically if we have a general hypercontractivity inequality over some space, it would imply that all low degree functions over that space are smooth. Unfortunately, that's not the case over epsilon product space. Over epsilon product space, there actually exist low degree functions that are very spiky. Unlike the case in Boolean, in the uniform Boolean hypercube. And the reason being that in the uniform Boolean hypercube, if we consider a very large subcube, this basically occupies a good fraction of this hypercube, and therefore is not very spiky. It's a kind of a smooth function. However, when we relax the condition to epsilon product space, we end up getting very small sets, even though when we're still considering the indicator function of some large subcube. This large subcube could have very small probability mass in this epsilon product space, and therefore the resulting function will be very spiky. So those are the functions that we precisely need to remove from our consideration, because we could not hope to show that they're smooth. So essentially, we require that all the function we're considering to have small correlation with those indicator of large subcube. The precise definition is given here, but it just captures the intuition that I was just talking about. Okay, so now after giving this definition, we're ready to talk about the proof. Here, for time constraint reasons, I will just give a proof overview, but hopefully this gives you some hint about how the entire proof goes. So generally speaking, our proof, as I mentioned before, relies on a degree decomposition of the functions over this probability space. Degree decomposition usually takes the following form. We decompose F into sum over S, F equal to S, where S is a subset of the sets of all random variables 1 through k. Okay, and we further note that we can rewrite the force moment of F to be the second moment of the function F squared. So, okay, and we can rewrite the second moment of F squared using the degree decomposition we have. We can split into sum over sets T1, T2, T1, T2, and S, all three of them subsets of 1 through k. F equal to T1, F equal to T2, and this whole thing, this whole product projected into the space F equal to S. Okay, so next we'll just trying to split these summands into three cases according to the relative relationship between T1, T2, and S. Note that these three sets are all basically subsets of K, of the universe K, and we split into the following three cases. In the first case, we have that the intersection of all three sets, basically this area, is non-empty. And in the second case, we want the three petals, this S petal, this T1 petal, and this T2 petal here, to be non-empty. And in the third case, basically when neither first nor second case actually occur, it means that all the elements, all these non-empty subsets are basically this one, or this one. Okay, so they're precisely the intersection of exactly two sets. So in this case, we know that actually T1 symmetric difference with T2 will be equal to 3. So this shows that these three cases basically covers every possible configuration of T1, T2, and S. Now, basically the main challenge is in analyzing the second case. And we'll see how it's different in the product space setting and in the epsilon product space setting. So basically, when we're considering hypercontractivity over product space, we know that, for instance, for the Boolean cube case, we have this Fourier decomposition, which is orthogonal and unique. And for general product space, we have the Efronstein decomposition, which is also orthogonal and unique. And here I want to maybe say a little bit about how the Efronstein decomposition goes. The Efronstein decomposition is defined using this projector operator A of S. So A of S, essentially what it does is it projects the function f onto the coordinates in S. So as f of x is basically equal to the expectation of f of y for all those y that have those coordinates in S having assignment exactly x. So f equal to S, this decomposition is defined precisely so that as of f is equal to summation over all t subsets of S, f equal to t. So this is the definition. And as we said, this is also orthogonal and unique decomposition. And precisely because of the orthogonal property of this decomposition, we have that all the terms corresponding to the second case are equal to 0. They all vanish in the product space setting. However, when we move on to the epsilon product space setting, we again have this decomposition as before. So we still have this f. We decompose it into f equal to s for every s subsets of 1 through k. And we still have this projection operator A of s, still defined as before. And using this as of f, we can define the f equal to t decomposition. We call it the approximate Efronstein decomposition. And the reason we call it approximate is because this time it's not precisely orthogonal, but it's epsilon close to orthogonal. And because of that, the second term here does not actually vanish. So we have to show that because of this approximate orthogonality property, we can obtain that the proof that the second term vanishes can still be adapted to show that basically this second term's contribution is bounded by the error term O of k epsilon delta times the second moment of f. And precisely because of this, we'll be able to obtain the final hypercontractivity inequality over epsilon product space with a small error like this at the end. Okay, so this concludes my talk. Thank you for listening. And we're happy to talk over email or during the poster section. Bye-bye.